The second part of our lecture, which is shear strength of soil, we studied in the first part of the lecture, or in the previous lecture, part of this, and we are going to continue now with the last part of our lecture, which is the shear strength. As a reminder, what we have studied, just to take a look of what we have studied the shearing resistance, or yes, we can say that the resistance of the soil of the soil to movement of any particle on top of it. It is because of two things, or two parameters. These two parameters, we found that they are the C and phi, or the friction and cohesion, and we said what is friction and what is cohesion, and how would we expect the shape of the soil to be. This is an explanation for, or illustration for soil particles, as if I'm looking under the microscope on soil particles. These are just small beads. These particles, if I put them on the ground, they will spread on the ground. They will not get connected to each other by any means. But if I manage to have some roughness for this surface, or as you said last time, if I maybe broke these particles into smaller particles, so the surface will be rough due to this cleavage surfaces. If I manage to just to add some roughness to the surface, and I pour these samples again, or these particles again, they may take this pyramid shape because they start to have friction on the sides. But if I add some kind of glue to these particles, they will get connected to each other, and I can make shapes out of them because of the glue. So cohesion is like the glue, friction is the roughness of the surface between the particles. These are the major two parameters, and we said that so the horizontal friction will be an effect for friction and an effect for cohesion, and we gave the equation, and we ended up with having this equation, which is the shearing strength of the soil is equal to the normal stress on the soil multiplied by 10 phi, where phi is the angle of internal friction, phi, plus C. This is the equation, and I think we draw. This was an example, some kinds of failures that would happen. This is the equation that we just discussed, and we said that this line is the graphical presentation of this equation. So this is the effect of C. First, this is the shearing stress, and this is the normal stress. So if I drew a relation between the normal stress and shear stress, so at zero normal stress, we still have the cohesion, because as we said, cohesion is like the glue. It adheres particles to each other without any it's always there. So this effect of C is here. So at a normal stress of 0, I still have some shearing stress because of the adherence between the particles and each other. Then when I increase the vertical stress on the sample, I start to have shearing stress. So depending on the value of phi, so it is the vertical stress multiplied by 10 phi. This is just a normal presentation of it. We took all of this, and we said that this is the normal shape of failure for any footing. usually if my footing is going to fail, then this is how I expect it to fail. The foundation will push this triangle below, and this triangle below will push these wedges at the sides, and these wedges at the side will push anything next to it up. So this is the normal shape of what I expect to be the failure of the soil. We said that it is called a general shear failure, and this is a presentation of it, and it happens with dense soil or stiff soil. But if the soil is weaker, then the effect will not move, because if the effect from the footing goes to this, and then from this to this, and from this to this to this, it means that soil is very strong, that it can push. It's not compressed by the load. But here, the load just passed from one place to the other and it stopped, so we call this local shear. And if the soil is very weak, this is the punching shear. I'm not discussing, I'm just reminding you of what we said. But in case you did not attend, then you will have to check the lecture to understand everything very good. We said if we have a sample like this and we put a load on top of it and a load around it, the sample is going to fail. But it will fail at an inclined surface. I don't know where. It may be this inclined surface. What is the value of this? It is theta. Remember that we have phi and we have theta. Phi is the angle of internal friction. It's a soil property. Theta is more or less a soil property, but it is the property that defines the angle at which my plane of failure will occur for this type of soil. So it's a different angle. Of course, there is a relation between the two. These were presented in Moore circle. Moore circuit are the circle presented by Moore. He presented this circle that can link everything together. It can link the C and the phi and the vertical stresses that we are applying, sigma 1 and sigma 3, and the induced internal stresses, the tau and the sigma, that will cause the failure of the sample. We'll just skip this. This is a drawing here. If I say this one is better. If you look at this drawing, you will find that this line is the same line that we were discussing before. Here is the C, here the inclination is due to the phi angle. So here is C and here is phi. So phi defines this line. C and phi defines this line. By the way, when we conduct the test of the shear tests, next time we will be asked to draw this line. We conduct the test to get C and phi, and or to draw this line to get C and phi. But if I connect this point to any point here with an angle phi, it will give me the normal and shear stresses at this inclined plane. So this is the difference between phi, this is phi. And theta, this is another thing. This is the inclination of the plane where I am going to get normal and shear stresses. Suppose that I define this point, a point here, that this is the failure point, then the shearing and the normal stresses are the stresses causing failure at this location. We'll just skip. I think last time we said that this is the shearing envelope, or the line causing the failure, and these are the circles resulting from the tests that I will conduct in the lab for the sample that will be sheared to failure. How can I determine the shear parameters? This is the start of our lecture today. How can we start? How can we determine the shear parameters C and phi? To determine the C and phi of the soil, I have many ways. I can do it at the lab and can do it at the field. In the lab, I have many tests. I have triaxial tests, I have unconfined compression test, I have direct shear test, and I have vane shear tests. But actually, vane shear test, it should be included with this, because vane shear test is a field test that should be included here. So number 4 here is added to this field test. So that's here vane shear test, but maybe this relates to vane shear test in case I conducted on a sample in the lab, but it is very rare. Mainly vane shear is conducted in the field, and also standard penetration test, which is the SPT test, and cone penetration test, which is the CP test. So you just know what are the tests that may result in having C and phi of the soil. What are the cases of this test? Right. Here we are going to discuss different cases of this test. We said that we can conduct some tests to get the C and phi of the soil. These tests differ according to the type of the soil. It differs from clay to sand. Can anybody tell me, this is not related to this lecture, why would it differ? Clay is different than sand. What do you know about clay that is different from sand? Can you by the way, I said it many times now. What is the difference between, the main difference between clay and sand?
Friction.
طب انت قلتي ايه؟ يعني it is something related to water, but it is the dissipation of the water. Water is not something bad. Water is something good in the soil. But the presence of water and being not able to leave the soil upon loading is a problem. So here, clay is a problem. Why? Because the permeability of sand is very, very low. So when it includes water and I put a load, water will carry the load. But I need actually the load to go to the soil, because this the soil will remain with me, but the water will leave me anytime. It's like you having two friends to help you. One of them is going to leave you in one day. So you consider not to depend on him. He's leaving anyway. But the other is staying. Then I will depend on the person who is staying. This is the same. Water can carry, but it's not staying. It will leave me in a while, maybe in years or maybe in days. So for me, I don't want to depend on water. I want to depend on the soil. So in clay, water will not leave very quickly. It will stay a while. So it will carry. And during the period of water staying in the sample, it will carry the load, and with the time, it starts to dissipate, transferring the load to the other soil sample. So this is what is happening. So cohesive soil, which is clay, is very important, because when it includes, of course, when I speak about clay, I mean clay with water, because clay without water, it's something like a rock, or a soft rock, you can call it. But this is not the case, because once water will come, it will behave differently. So I have to simulate my structure. My structure, when I put my structure on the soil, it will behave depending on the type of the soil. If I have clay with water, then I have to study two cases or maybe three cases. The first case is the very quick case. Once I put the load on clay with water, what will happen? Water will carry a little bit. So I have to study this case, which is the case of water not leaving the sample, and I call this undrained condition. Why undrained condition? Because water is still not drained from my sample. So this happens in reality, it is immediately after loading. All external stresses are loaded on the groundwater only, because just when I put the load, the water is still there and it will carry everything, because my sample wants to be compressed to take the load, but it cannot be compressed because of the water. So what will carry the load is the water only. So this is what we call an undrained condition. Since water is still in the soil and therefore no friction occur between the soil. How will friction happen between soil particles? If I have water all around the sample, so there is no friction. So in this case, I have to take phi, which is the frictional angle, is equal to 0. Though in reality it is not equal to 0, but at this specific time, it will be 0. And the resistance of the soil here is due to cohesion only. So only cohesion will work with me. So in this case, I have C, it will be equal to something called Cu. Cu denotes to C undrained. It means that the cohesion of the soil in case water is still present and it is not drained. And in this case phi, it will be called phi undrained, but it will be equal to 0. Why? Because water is there preventing friction from happening. The other extreme, when I leave, I take all my time. All of the water is dissipated. So what happens? We call this a drained condition. A drained condition, it happens after a long period of time. All external stresses are loaded on the grains of the soil due to the release of a sufficient amount of groundwater. Of course, not all the groundwater is going to leave. Part of the groundwater is going to leave, the adequate part that is enough for soil particles to come in touch with each other again. So water has left, excess water have left, and I end up with having water, but I have the phi angle again in place, because particles of the soil are now very close to each other and they can exert the friction between each other. So the shear resistance here is the result of the friction between the soil particles and cohesion between the soil. Cohesion is also there because it was there at the beginning, it will still be there. So in this case, I will have something called C dash and phi dash. At this, we have Cu and phi u, and we said that phi u is equal to 0. In this case, which is at the extent, the end of the loading, I will have something called C dash and phi dash. What is the difference between C dash and C? And what is the difference between phi dash and phi? I just eliminated the effect of water. I will have to, if I want to put an equation, I will say that there is something called the effect of water, and it will be C, it will be equal to C dash plus the effect of water, and phi, it will be equal to phi dash plus the effect of water. Okay, so then this was cohesive soil. So in case of clay, I have two cases, at the start and at the end, because clay, as we said, that it has a very low permeability. What about sand? Sand has cohesionless soil, which is cohesionless soil means sand or gravel. Sand or gravel, it means that water can leave anytime at the early start. So I don't have cases, I only have one case, and in this case, water will be expelled immediately. So it will be more or less similar to this case, 200% consolidation, but it happened in seconds after exerting the load. So in case of cohesionless soil, water quickly leaves the soil due to its high permeability, and the stresses are loaded directly on the soil. So in this case, I have C dash and phi dash, and they are not equal to 0. That's all. Laboratory testing. How can I test this in lab? We said that in reality. This is in reality. This is loading a building in reality. But what about in the lab? I want to simulate a case of loading in the lab. In the lab, we have a test called triaxial test. Triaxial test is a very complicated or elaborated test. It's very good. It simulates any condition. By the way, this is one of the very expensive tests in any geotechnical lab. What does it include? Imagine with me, you can understand this very easily, even if you don't understand the previous, you did not attend the previous lecture. Because it's just a test. I have a sample in the middle. This is a soil sample. This soil sample, I want to affect it by two kinds of load. I want to affect it by load confining, a load surrounding the sample. If I tell you something, I will give you clay, and I will tell you, put this clay on the table, push it down. You will find that you can easily push it down. But if you bring something and you wrap this clay all around, and you try to push from up, it will be very difficult for you to push or compress the clay, because something is preventing it from extending to the sides. So this we do here. We bring water and put it inside so that it surrounds the sample from all directions. Surrounding the samples from all directions means that water is pushing on this sample. So it is actually preventing this sample from extending laterally. Can you follow me in this? Okay. So this is the first type of loading. The first type of loading is that the sample is surrounded with water, and this water has a tap here. If I close the tap and put water inside, it will compress the sample as it is, and water will not leave. But I also have another tap at the other side. This tap is connected to the sample itself. It means that if I have excess water inside the sample and the water wants to leave, if I open this tap, water will leave. If I close this tap, water will not leave. So it means that this tap controls what we said, the permeability. Because if I close this tap, then it resembles clay with very low permeability, because water is not allowed to leave. If I open the tap, it resembles sand, because water can leave anytime it wants. So opening the tap, this tap means that I am free, water is free to leave the sample anytime. So in a triaxial test, the test utilizes cylindrical soil specimen, which is enclosed By the way, it should be specimen or sample is good because we are conducting a test now. So it is a specimen, correct, which is enclosed in an impermeable membrane, which in turn is securely bound to the base of the to a base and cap, and place porous plate above and below the sample to control the exit of water. So water can exit the sample from here, and it will end up from this tap if I compress my sample. This is just a description, and of course I will measure this. This is the first load, which is the confining load. I have additional load. What is this additional load? This load on top. I can bring a piston to compress my sample from the top. So actually I'm doing two types of loads. There is a confining pressure all around. This is, we can call it sigma 3. Sigma 3, we said from the previous lecture, is the stress that is confining the sample or all around the sample. Sigma 1 is the very high stress that is exerted on top of my sample. So here is sigma 1, and sigma 1, by the way, is the stress that causes failure. Sigma 3 is the stress that confines the sample together, and it would not cause any failure, because the sample, any sample, to fail, it means that I have a stress from one side, and from the other side it does not have a stress, so it will be sheared. But if I have compression from all around, it will never fail. So in this test, I have water, it resembles sigma 3, and I have this piston, it resembles sigma 1, and I can measure the deformation of the sample, how much the sample is going to be compressed. The steps of this test. First step, loading the sample and stress with stress equal to sigma 3 from all sides. This is what we said, that we are going to push or to insert water inside this space, so that water would push the sample, but it will push the sample all around, from all directions, and even from the top, it will, and the bottom. It will push the sample all around. So when I use this tap and push water inside in high pressure, and then close this tap, then it means that my sample is now compressed with water. I will stay like this. If I open this tap, then I will allow the sample to consolidate. I will allow water to leave the sample. It is as if I am acting that this sample is sand. But if I keep this tap closed, then I am resembling a sample of clay that water is not free to leave. And this will be at the early start of the loading in reality. So I just here put sigma 3, which is the water, all around the sample, and the sample is now exposed to sigma 3 only. To continue this test, I have two ways for continuing this test. Either consolidated test or unconsolidated test. From what I said now, if I want to have a consolidated test, it means I want to do what? Consolidated. Yes, I need to open the tap so that water can go to resemble the consolidated case. So consolidated test, it means to allow water to exit the sample through the opening of the water, open the valve, that's all, or the tap. Then waiting for 24 hours. So I will open it and I will leave it for 24 hours so that all water can leave this sample. So in this case, it will be a consolidated test. Unconsolidated test, then I will keep this closed to allow, we do not allow water to escape the sample by closing the water exit valve, and thus the external stresses are loaded on the water only, not on the soil particles. We said that if water is not allowed to leave from the beginning, then all the additional forces will go to the water. So I'm trying to resemble in the lab the real conditions of the soil inside. And this is the importance of this test, because this test, with this test you can resemble any performance of any sample: clay, sand, early start of test of loading, middle loading, end of loading, anything you can resemble with this, or you can model with this test. So what are the steps? The second step is that after completing the first stage was adding water with sigma 3. Now I need to begin to increasing the stresses in the vertical direction by operating the piston that moves down at a constant speed. So now I have here a piston that can move at a constant speed. When I move this piston, it means that it will start exerting vertical stresses on the sample. So this is called sigma 1. So this is while measuring the increase in the vertical stresses affecting the sample with time, so I will measure the stresses and measure the time with the time, and I will also measure the settlement of my sample, as well as determining the settlement occurring in the sample with time. This stage continues till failure of the sample. So I will start pushing till finally I get failure. From what you have seen before, how do you expect the shape of the failure? How will this sample be sheared? Do you remember? What will happen? What will happen really is that this sample will start at the beginning to bulge a little bit, because you are increasing the stresses here, and the stresses want to go radially. Then when I reach a certain limit, I will find that the sample is going to be sheared in a plane that have an angle. You remember what we have just said here, where this one, this layer, this plane, that due to sigma, here you see here, this is sigma 3. Sigma 3 is similar to the water that I was adding to the sample. Sigma 1 is the stress of the piston. So I try to increase sigma 1 till I have stresses at these inclined planes, and then when one of these inclined planes reach the failure, the sample will be sheared like this. So this is exactly what will happen here, that my sample will be sheared like this, and this will be the failure of the test. How I know the failure? I will find that the deformation I'm measuring suddenly increases sharply. So this is the second step. This second step can be conducted also in two ways. So the first step was conducted in two ways: consolidated or unconsolidated. The second step will be conducted on two ways. We call it drained or undrained. So it means drained or undrained when I put the vertical load. I put the vertical load, either I open the valve or the tap, or I keep it closed to allow water to exit the sample through the opening of the through the opening of the water exit valve, taking into account that the loading rate is very slow until water exits and thus external stresses are loaded on the soil particles. So to have the drain test, I will open the tap, but in this case, try to put the load very gradually so that increasing the load would match the water leaving the sample, because if you increase the load very quickly and the water still did not leave the sample, so you will be getting wrong results. So to get good results, you open the tap and you allow water to drain and put the load very, very slowly till you reach the failure load. The undrained, I just close the tap, that's all. We do not allow water to escape from the sample by closing the water exit valve, and thus the external stresses are loaded on the water only and not on the soil particles. So in this part of the test, I just, it's either I open this valve or close it. If I open it, then water will be allowed to leave the sample. So when I push this sample with this piston, the water will leave till I reach failure. The other one, no, I will close here, and the water inside will carry the additional load, and the sample will be sheared also. It will be sheared, but in this case, it is not the condition, the final condition, it is still the condition where water is still carrying part of the load. So this is the second, as we said, drained and undrained. Then here you can draw a relation between the deviator stress, which is the sigma, the additional stress that I'm adding on top, and the time of the settlement. And from the graph, we determine the value of delta sigma at collapse. I go, where is the failure at this point? Then this is the failure. Of course, I can determine it without the graph, just by following the test. Once I find that there is the stress started to decrease, it means that there is excessive settlement happening, and it means that this is the load, the stress that caused the failure. You have to take into consideration that we said at the beginning that we have sigma 3, which is the water, all around the sample. So it is coming from the sides, coming from top, coming from bottom. And then I started to add the stress on the piston. The stress on the piston is called delta sigma. So to get sigma 1, which is the vertical stress, it should be equal to what? It should be equal to sigma 3, because as I said, sigma 3 is horizontally and it is vertically also, it is there because water is pushing all around. If you jump in the water and you go down 2 meters, water will be pushing you from all directions. I cannot say that the water is going to push me from the sides. It's also pushing my head, and it is pushing my feet, it's pushing everywhere. So this is a sample in the water. So the sample in the water is being pushed by water in all directions. So to get the vertical stress, so I should add the stress that I have added myself, plus the stress of water that was there all the time. So this is sigma 1, which is equal to sigma 3, plus the delta sigma that I have added due to the piston. Then I repeat this experiment many times. 3 times is okay, to get different values to be able to draw charts. These are the charts that I want to draw. If you remember, we said that before, that this Moore circle, it has here sigma 1, which is the major stress that was applied, and here sigma 3. So it means that to repeat this test, I will repeat it, say 3 times. How can I repeat it? I will go here, add water inside at a certain pressure, and then close this tab. When I close this tab, then I am keeping here sigma 3 all around. And then I start to increase the stress with this piston. When I increase the stress with this piston, what will happen? I will, after a time, reach failure. Depending on the type of the test, it is either I open this tab or I do not open this tab. It's not my problem now. But when I add this stress, I add this stress till I reach failure. So this is one cycle of the test. I repeat the cycle with different confining pressure, with different sigma 3. I will add more water inside, so the stress will be more, so sigma 3 will be more. Here, I will ask a question. If I get an answer, I will be satisfied. If I don't get an answer, then I will give you the answer myself, because I need you to know it. In the first test, I had sigma 3, which is the water pressure here. And then I pushed here till I reached failure. Say failure happened at a stress of 10. If I increase sigma 3 by adding more water, what do you expect the value of the stress causing failure in the next case? I mean, for the first case with small value of sigma 3, I got a failure of say 10. If I increase the confining pressure, which is sigma 3, would this 10 increase or decrease? Increase or decrease? You said decrease, but you said decrease because this is the normal logic of thinking, that when I add the load, the sample will fail. But I want you here to feel the difference. Sigma 3, which is the confining, is the something that helps the sample to be stronger. When I increase the confining pressure, it means that my sample is now stronger. To shear it, to put a load to break it, I need higher load. I need higher load because sigma 3 increased. It is like, I will give you something to think of it. When we are small and we are just facing life, if you have many problems in your life, you will end up being very strong because you have already faced lots of problems in your life, so you are now strong. But if you are spoiled and everything, you have everything, you don't have experience, you cannot face the life because you are not exposed to pressure. So soil is like us. When we expose soil to pressure, it can carry more. But this pressure has to be from all directions, because I want the pressure not to exert any shear. I want it only to increase my normal stresses. So when I have shear, I have pressure on my sample, then the sample can carry more. This is how you will find this. Look at the drawing. The drawing will tell you here. This resembles sigma 1 and sigma 3 of a sample that was failed. And this resembles another cycle with a sample that failed. And this resembles another cycle with a sample that failed. By the way, all the samples are the same. If they are sand, then the three are sand. But the difference in what? The difference in the confining pressure sigma 3. Here, sigma 3 is this value. Here, sigma 3 is this value, it is more. Here, sigma 3 is this value, it is more. The higher value of sigma 3, follow this circle, go here. This is the highest value of sigma 1. So the higher confining pressure needed higher vertical stress to fail, and so on. So when we increase sigma 3, then we expect sigma 1 to be more because of this shearing envelope, because I have phi in my soil. This phi makes this line inclined, and in this case, any circle I draw outside away from the zero is bigger than the previous one. When I can say that I will not have any effect, all the samples will fail like each other, if I have this line, instead of having an inclination angle, I have it horizontal. If I have a horizontal, it means that if I have phi equal to 0, if I have a phi equal to 0, angle of internal friction equal to 0, then my line will be a straight line, a horizontal line. In this case, any circle you draw will be similar to the other one, but even in this case, I will have different values for sigma 1 and different values for sigma 3. We'll discuss these different shapes later. What are the tests that are done using, if I go to this experiment and I want to conduct these tests, I should have some standard. They divided these tests into 3 categories. Just to expect what we are going to have. I need a test to resemble the start of the test in case of clay. And I need a test to resemble the end of the test in case of clay or the sand, because it's not important. Sand does not require any the start of the test is like the end of the test. And I need a test in between to give me an in-between case. So I have 3 types of tests. It's either unconsolidated, undrained. Remember here that we spoke about opening the valve twice. One for the confining pressure, after putting the confining pressure, and allowing the sample to consolidate or the water to leave. The other one is after applying the sigma 3, the sigma 1, and allowing the sample the water to leave. So I have the first type of test is called unconsolidated, undrained. It means that in the first case I did not open the tap, and in the second case I did not open the tap. So we call this the quick test because the taps are always closed. I just put water, then I add sigma, the stress of the piston, and the test is finished. And I just increase it till failure. I don't want to wait for water to leave. So in this case it is, and this case resembles what? Resembles the case of clay with water at the early start of loading. I have soil with water, clay with water, and I put my load at time 0. Time 0, this what will happen, so this test resembles this case. This is exactly what I said, that sigma 3 I don't allow the water to leave, and sigma 1 and I don't allow the water to leave. This is the shape of the test, by the way, the one I've just told you about, that here I have phi equal to 0. Why phi equal to 0? Because water is not allowed to leave. So water is carrying the load. Water has no shear stress. So phi of water is equal to 0. And if I conduct this test 2 or 3 times, it will give circles that are equal to each other, equal in the difference between sigma 1 and sigma 3. But if you increase sigma 1, sigma 3 will increase accordingly. So this is the shape of the results of this test, which is the quick test or the UU test, which means unconsolidated, undrained test. The second test is called consolidated, undrained. Can you expect what will happen? If I say consolidated, undrained. The previous one was unconsolidated, undrained. If I say consolidated, undrained, it means what? Anyone? It means that water was allowed to leave in the first stage of the test. which is the stage of water, of the confining pressure of the water surrounding the sample. So I allow water to go inside, and the sample, I allow it to consolidate. Water is going to leave the sample. Then when I start to put my sigma 1, which is the stress coming from the piston, I don't allow water to leave. This happens where? Suppose I have soil that is preloaded. There was a building on this land, and I demolished this building. So the soil below is consolidated. Why? Because I added the load a long time ago, so water is consolidated. And then I remove this building and I put higher building. What will happen? The higher, though the soil is consolidated, but the higher building is now at the start of the consolidation for the new load. So this is the case of consolidated undrained. You see, the advantage of this test, it can simulate any case of loading in the site. So consolidated undrained means the sample was consolidated due to sigma 3, and now it will not be consolidated due to the or not going to be drained due to the additional load that will be put. So we describe this. This is the shape of the results of the test. I will have phi and I will have C, but here we call it consolidated undrained. So this is phi consolidated undrained, this is C consolidated undrained, and these are the results. Of course, in this case, it resembles an intermediate case of construction, because later this undrained will be drained. If I leave the example that I have said, I demolished a building and I put a higher building instead of it. This higher building will once cause the soil to consolidate and all the water will be expelled. So I need to study another case at the end of the consolidation. Maybe after 70 years, 30 years, I don't know when will be the end of it. So this will be my third test, which we call it slow test or consolidated drain. It means that all load I put, I wait for the soil to consolidate. I will put sigma 3 and wait it for 24 hours to consolidate. Then I put the piston to add sigma 1 and wait another 24 hours for the sample to consolidate. Of course, here we say 24 hours, not years, because it's just a test in the lab here. To get rid of all of the water inside the sample, because I'm going to choose a sample that can consolidate easily a little bit. Of course, if I am forced to use any sample, but this is the procedure of the test. So this is a description. This is the result of the test. If you compare this to that, more or less it is the same. But the difference will be in what? The difference will be in this. This is called phi dash, and this is called phi consolidated undrained. The value will be different. Which one I expect to be more? Of course, this phi will be more. Why it will be more? And this C will be more than this C. Why? Because I expelled more water from the sample, and the soil now is ready to carry more. It is now, the soil is completely carrying everything, not the water contributing in carrying part of the load, and we said that water cannot carry shear. So now if water is expelled, then the sample can carry everything. These are the three tests. I'm sorry I had to discuss it in details, but when you hear both lectures again, then or the whole lecture again, you will understand this very, very easily. There is another type, similar test. you are going to use a similar one in your concrete lab. In concrete lab, you are going to take a sample, put it in a piston, and it will be loaded till failure. In my triaxial test, I can simulate this. How? I will put the sample, but I will not put anything around the sample. Water is not going to be put. And I will just put the piston. So we call this unconfined compression test. It is equal to what you do in your concrete lab with the concrete samples. But of course, this is just for soil. I put the soil sample, I increase the load, the sample will be shear. What about this test? For this test, I know that sigma 3 is equal to 0 because I don't have any confining pressure, I only have vertical stresses. So this is the drawing of this one. When I say that I don't have sigma 3, then it means that my drawing will, all my drawing, my circles will be here. I have always sigma 3 equal to 0, and I have here sigma, this is the value of C. So all my, any test you are going to conduct will be something like this drawing. So just for understanding. Last part of this lecture, the last part of the lecture is the direct shear test. The direct shear, you will have a separate lecture for the direct shear, which is the next one, and you will conduct the direct shear yourself. So we'll just take a minor introduction for this direct shear. Just to show you something, I want to show, to make a comparison between the direct shear and the one that we have just said here, which is the triaxial test and the different shapes of the triaxial test. The direct shear, a container having a sample, and this sample is put between two rings, an upper ring, or imagine that you have a cylinder, but this cylinder is consisting of two parts, an upper part and a lower part, and I put my sample inside. If I put my sample inside two parts or two cylinders, and then I push the upper cylinder, what will happen? My sample will be sheared, because the lower cylinder will stay in place and the upper cylinder will move. It may be cylinder, it may be square, or square in cross section, it's the same. But what I mean, I have a soil sample with a fixed container at the bottom and a movable container at the top. And I move this movable container, ending up with shearing the sample. What I want to stress on, because this is really something that you may not hear in many places. I don't like the direct shear test. Why I don't like the direct shear test? Because in the triaxial test here, I was pushing the sample here, and I am leaving the sample to choose which plane is the one that causes failure. The sample is free. It may this plane may be sheared. This plane, any plane, maybe in the other direction, it may be sheared like this. Who knows? But in my case of the direct shear test, I am forcing the sample to be sheared on a specific plane. This is not good because it does not give me the correct value of C and phi, because maybe it is not this plane that is causing the shear. Maybe my sample would prefer to be sheared like this, but I am forcing it to be sheared horizontally like this. So I am inducing the plane of failure, and this I don't like. So usually when I conduct a direct shear test, I get higher values of C and phi, because I'm shearing the sample on a specific plane. This you should take into consideration. But it is very good for comparison, because if I have two kinds of samples, if I have clay and sand, and I put a sample of clay in this sampler, and I put a sample of sand, and then I get here a value of C and phi and a value of C and phi, then the comparison will be very good, because I'm comparing apples to apples, oranges to oranges, but not comparing the result of C and phi of a material from triaxial test with the C and phi of another material in a direct shear test. Then I'm getting different values. So this is what I want to stress in this lecture. The procedure, we will discuss it later, because we are going to put 3 types of samples here, and we are going to shear the sample. We are going just to push the upper part of the sampler and measure the deformation or the shift that is going to happen. And I'm going to, once I reach the failure, I just push till I reach a failure. Then I record the failure. Of course, I will have a vertical stress here. This is, I forgot to tell you, that I can put different values of vertical stress on top to increase the value of the shear of this force that is required for shearing. So I will conduct the test many times, say 3 times. Every time I will get different values for sigma n and tau. I will draw these 3 lines. Then based on these 3 lines, I will draw the shear envelope. The shear envelope will cut this line in C, and in this line at phi. I can also put water or do not put water. If I put water, then I'm taking the effect of water. If I do not put water at all, then I'm not taking the effect of water. Anyway, so I may get C dash and phi dash. I can, by making it a very slow test so that the sample would consolidate. This we'll discuss very easily next lecture. But what here we need to know is these are the results of, this is an example. I have 2 specimens. These specimens have different sigma 3. What is sigma 3? Sigma 3 is the value of the stress due to this load. I put a load and I put a higher load. These 2 loads, I have these 2 loads, and then I put the additional load here that will cause shearing of the sample. The first sample I needed for a confining pressure for sigma 3 of 200, I needed 150, and I have 300 for this 400 sigma 3. And I have this value of the water pressure. And he tell me, draw he wants me to draw these circles and for the effective stress. What we are going to calculate here only is something due to the effect of water. If I have sigma 1, first how to calculate sigma 1. Sigma 1 is sigma 3 plus delta sigma. This is similar to what we have done in the previous tests. Sigma 1 is the total of the confining pressure plus the additional stresses that I have put. So now I can get sigma 1. How to calculate? So now I have sigma 1 and I have sigma 3. How to calculate sigma 1 dash and sigma 3 dash? I subtract the effect of water. So to get sigma 3 dash, I take sigma 3, which is this one, subtract from it the effect of water, I can get sigma 3 dash, and so on for sigma 1. So now I have sigma 1 dash, sigma 3 dash, sigma 1 and sigma 3. I can, using these values, I can draw 4 circles. Using these 4 circles, each 2, the one with the total stresses, I can draw this line, and for these 2 circles I can draw this line. From this line I can measure the value of phi, and of course the result here shows that C was equal to 0. it's not always this case. Maybe in another example you would have this line crossing at this point, so I have a value of say 50 for this C. We can stop here. We took it very quickly. When you study the next lecture and then hear this again, it will be very easy for you, inshallah. Thank you and see you next lecture.